Alrighty, let's get started. As you know, I'm one for speeches about attendance. The attendance is low, probably because of the videos that we do, but it is what it is, so I'm going to skip the speech. Okay, so today's the last lecture on the Fourier expansion or applications. Okay? And some we've already talked about, but maybe less formally. So there's just this thing that sometimes it's good just to mention, right? This isn't on the exam, but it can kind of come up and cause confusion. And basically, what are we doing? Are we using Laplace? Are we using Fourier? And so the thing is, the answer is yes. But what happens is the Bode plots are more Fourier than Laplace. Okay, and we'll just, okay. So let's just do a transfer function, right? And we'll just do a low pass filter, right? Now, what is S, right? In control theory, S equals a real number plus an imaginary number, and we plot things on the complex plane. And so when S equals -1, let me do a different color, right? Okay. And now forgive me for my terrible drawing, what I'm about to show you. So that's a pole because it goes to infinity. And yeah, if you kind of play with the plotting of it on a two-dimensional plane, right? And now this is the z-axis, you would see a pole there, right? But all the, whatever algebra and Laplace transforms that gave you that transfer function, that's the transfer function. Great. Now, but we also do this with Bode plots. So again, I might have said the words, but sometimes we're just not ready to receive. So take this axis and rotate it, okay? And instead of calling it j omega, we just call it omega, even though when we would actually hand calculate the Bode plot, it would be j omega, right? The other thing we do, so this point goes there, this point goes there, but yeah, now we do a logarithmic of the axis, 0 not allowed, right? And then here we do 20 log of whatever's going of the magnitude, right? So we get a something like that. Okay, but how are we? So I just showed you we mechanically did that, but I'm just going to expand this axis a little bit, omega. This is the input, right? And that means the input is a sine, are all sine waves. So let's call that, 1 radian per second coming in. And then over here, I'm going to try to, it's a bad sine wave, right? 10 radians per second. And then in between, right? So the inputs are all sine waves. inputs, all sine, phase equals 0, right? And exist forever, right? They exist, they exist before the beginning of time, after the beginning of time, to the end of time, if that exists. Maybe we're all in a loop. What do you mean by the same?
Like, if you're, is there like a specific language that is like a standard that this is this particular and
I mean, everything, yeah, okay. So the question is there a standard sine wave in telecommunications? Um, well, if you just look at a cell phone tower, there's bands of frequency that are that are used. So it is standardized, but it's not just one frequency. It's bands of frequency. And yeah, that's the FCC. And when somebody wants to can only sell that bandwidth to kind of one entity, right? Um, unless, at a time. So like certain frequencies are for cell phone carriers. And yeah, there's a lot of work to go into our phone calls not overlapping each other, right? As we call, even old wired things, all right? And that's something called modulation, which is an application, and we'll talk about that later. All right. So, and then just to bring it back to the expansion, here's a 50% duty cycle, and we're saying it repeats forever. And then we kind of get a spectral analysis where this was 1/2 because it was 50%. Then we have F1, which is 2 over pi. This is the amplitudes, by the way. F3, 2 over 3 pi, and so on and so on. And yeah, I've now kind of switched to frequency rather than radians. But these are all done linearly. Both scales are linear, right? And it's the signal. The Bodie plot is the system, okay? And so the signals go into the system. Now over here, like a Bodie plot, we have all the frequencies there. But if we input a square wave into a low pass filter, all the frequencies aren't there. What's input is this pattern, depending on what the fundamental frequency is. All right. But this spectrum is Fourier and everything exists for all time. The Bodie plot is Fourier, everything exists for all time, and all frequencies are there, right? The Bodie plot is Fourier, pole zeros and controls is Laplace, even though we kind of use them interchangeably, right? Mathematically, that's not correct, but it's so useful and you go back and forth so much. So now that we've got our, that, right? I just want to go over the pulse width modulated DAC just a little bit more. So this is the duty cycle changing, right? and we talked about the average, right? So the average, and what's not shown is that it's repeating. But this is on for 1/8, 2/8, and so on and so on. So the average is 1/8, 2/8, so on and so on. And when you filter it with a low pass filter, you would get this step. Now, what's wrong with this picture is these time scales are not the same. Is that this is caused, this first step is caused by this repeating, and you can see that it's repeating, right? So you repeat it and you filter it and you get it. Then you change to 2/8, filter it, repeat it, and get it. But if you're kind of, what you would have, all right, and I think I can show, I can draw it a little better, which is saying something. Okay, is that I'm trying to do 1/8, right? Then I'm going to switch to like, I don't know, 3/4. So I'm just saying, between here and here is 3/4, and here is 1/8, right? And so what'll happen is, but rather than 3, I'm going to say there's 20 cycles there. And rather than 3 there, I'm going to say there's 20. So now I'm not on the same axis anymore, same time axis. So this will bounce up, and then it'll start to oscillate at 1/8 around that. And then over here is a 3/4. Then when I change to 3/4, you'll see this jag, and then it'll be at 3/4 in time. And what you can do is change this pulse width modulated thing with a sine wave, and you can get ultimately a sine wave, right? Not the same time scale, right? But as you're going to see, is if I have a fast time cycle and a low pass filter, right? Ultimately, it's going to average, it's trying to find the average of that, and it goes up to a half because I have a half duty cycle. And here's the thing, if it's a first order filter, it takes 5 tau to do that, right? Now, what if I have a slow thing, right? Well, what happens is you get the step response. And so when it's faster than the cutoff frequency, it'll average to what you want, but basically this is passing the whole signal. And so you end up choosing the right frequency to get this shape. But this will be 5 tau, and this will be 5 tau as well, except that the 50% just goes 50%. And this ripple I'm talking about is the worst for 50% duty cycle. So this ripple is actually the minimum amount you can discern of a signal. And so let's say I'm rippling like this. So that's my uncertainty, right? And so if this is my VDD and this is my ground, I'm just eyeballing it. 1, 2, 6, 6. I'm trying to draw these the same distance, okay? So that really means I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12 levels. That's because this ripple is so big, I can only fit in 12. If the ripple was smaller, I could fit in a lot more. And so the effective number of bits is log 12 to the base 2. So, you know, what, 2 to the 3. So a 3-bit system gives you 8 levels. A 4-bit system gives you 16. So we're in between 3 and 4. And so what you're going to be finding is what is the best frequency and what is your effective number of bits for the project. And how are you doing that? You're choosing a filter, right? What's the order, right? How sharp is that? And then what's the type, right? This is like a Butterworth filter, but there's other filters that kind of do that. So there's Butterworth, elliptical, and 2 others that you can use the analog device wizard, and it'll tell you what it's doing. When you change the spec, it'll change what kind of thing you're using, and we're going to talk about that just a little bit more later. Okay. All right. So again, if I have a DC and a a square wave with no offset and add them together, right? You can see that there's a DC part. And this green, right, is the waveform I'm talking about. And here's a fundamental frequency. Here's a sine wave. And you can see the error, right? The sine wave is trying to approximate that, right? But so it's kind of like a square wave, but it's not a good approach. So now here's our Bode plot. We're at 10 kilohertz. Here's a cutoff frequency of, I forget. Anyway, you can see that I put in V in and get V out attenuated, right? That looks great. But then I put in a square wave and I don't get, right? I get this kind of triangle thing. That's because it's going up for the step response, but I turn it off before it plateaus and it comes back down. And then that's just a sine wave, right? And now I change the cutoff frequency again, and you can see that the sine wave is there. Like if I input a sine wave, I get a sine wave. And you can kind of see the DAC is having this triangle, right, from the square wave, and that's the ripple. Okay. Then I try a second order, right? But this is very close to being overdamped, all right? But you can at least see that the slope is sharper, and you can see that the ripple is smaller. So I can get more levels, I can get more effective bits. All right. This is more. So there's a trade-off. And this is more the project, okay, is that this is the frequency of the pulse as we go back and forth, right? And then there is a clock frequency. Well, there's a clock frequency, right? And then there's a PWM clock frequency. And if FC goes up, this is going off and on more, and it gives you more control, right? So the smaller this is compared to this is FPWM. So the bigger this is, the more clocks I can get in there, the finer I can control. So this is effective number of bits, right? And we get 0 when we are at the same clock frequency, right? And so the slower this is, the more clocks you can fit in, the more effective number of bits. That sounds great. But the cutoff frequency, right, as we're moving it around, right, if it's too low, it's not allowing the data through, and it's the opposite way, okay? So the cutoff frequency of the clock, you want to let through as much as you can, right? And so you end up taking the geometric mean, and right here in the middle is like F max, and this would be the effective number of bits. So this is all in the lab manual, and I think it's better to do than to hear me talk about it, right? But it is this trade-off, right? And the thing, what's nice though, is this region is very flat. So changes in clock frequency don't affect the number of bits that much, right? But the higher order of filter, right, should make a sharper FC, right? The higher the clock frequency in the system, the farther this will go out, right? So I've been, in all the examples, I use 16 megahertz because that was the microcontroller I had at the time. But they make other ones, actually even TI makes ones with like a 200 megahertz clock, but they were doing all these tricks that I felt I couldn't explain in class. So I just kept it to 16, right? And you can just see this, I know I'm doing this. I'm just going through, this is the step response of the filters, and then now I increase the clock frequency, and notice it's wiggling up and going to 50%, and you can see the ripple. Now this is a second order filter, so there isn't a 5 tau, but you can see that it looks like the step response of a second order filter. And that's zoomed in, so it's not quite a triangle, right? And I have a huge derivation in the manual that you can follow, right? So we can use Fourier to actually test things in a very formal way, right? Now, So if this is your times table, right? No, this isn't right. Zero times zero is zero, right? One times one is 1, 4, 9, 16. And then you can fill in the table, right? In order to test it, you have to test all those values, all right? So now we have an analog multiplier, which we just call this. We have y and x, their inputs, and usually it's x times y plus offset, all right? And the AD6, no, what is it? The A, I think it's 680, is a multiplier. And so it's not like multiplying by 1 or 2 like an op amp, non-inverting op amp. It's actually multiplying, right? And so you have this input, and then you got to step y1, y2, y3, and then here's the output, right? This times that divided by 10, and you just, so you hold y constant, and you sweep x, and then you get values. So that's very complicated and is a long test, all right? Now, what we can do is, here's our multiplier. I'm going to tie the inputs together, and I'm going to put in a cosine 2 pi f p, right? Now, this is now cosine 2 pi f t squared, right? So I have this function, and it's going to kind of give us twice the frequency. Now, you can find the Fourier expansion of this or use the trig identity, right? And I think it's going to be, the offset is going to be positive because now you're squaring it is practically taking the absolute value, right? So it's going to be 1/2 minus cosine 2 pi f t times 2. All right. So if I take the FFT of this, and it's a kind of a perfect thing. Oh, and I think this is divided by 2 as well. I have to look it up. So if I take the FFT, or do the Fourier expansion or whatever, right? I get half, and then I get half at 2. I'm just going to call that FO, right? 2FO. And so if this is perfectly a half at 0, and this is perfectly a half here, then that multiplier is working, right? And if I change the frequency and the multiplier can't keep up, you'll see it here, right? If I make the multiplier too big, where it's clipping, right? Well, these discontinuities will be easily picked up by having like, infinite spectrums. So if I see two, it's great. If I see these, right, if I see extra things, right, then it's not working. And when you measure the things you don't want versus the thing you do want, that's total harmonic distortion. But it can be a little bit tricky because it really is based on what the fundamental frequency is. And let's see. Oh, oh, I did it already. Okay. So here's an LT Spice code, right? And I just have Vn squared, right? I'm just making an ideal, all right? And the green is the original, Vx ideal is blue, and you can see that it's twice the frequency and it's not being, altered. And then V out 1 is clipped, right? So those corners are going to cause a lot of harmonics. And so look, V in, we have 1 kilohertz, and it would be, if I converted it to amplitude from RMS, it would match. Then Vx ideal, you see it at twice. And again, I would just have to convert it to get the 1/2. But now look at V out. You see those harmonics creeping in. And really, you just have to think, this is the square wave, right? And you know that the coefficients Vn equals 2n pi, n equals 1, 3 to infinity, right? And it's because, and you remember that the sine waves, right, as you try to get closer and closer, right, you see these extra sine waves trying to approximate that change, right? So if I had a ramp, that kind of change will cause infinite frequencies, right? Now, if I have something like this, it kind of looks like there's two sine waves there. So I'll only get two sine waves, all right? And you can run total harmonic distortion on that. And it gives you the frequency, the Fourier component normalized, and it's total harmonic distortion, 0.187%. That's on ideal. And the non-ideal one shoots up to 12. So now, really, that can be automated. Right? You have the ADLM that does the Fourier spectrum, which well, I don't know if you know, but you can control that in Python. Which it can change the frequencies, change the amplitude, measure it, calculate the total harmonic distortion, and step it until it hits. You say, well, the total harmonic distortion has to be below 1%. So you change the amplitude and frequency until it exceeds 1%, but you can do that automatically. Go have a cup of coffee, or maybe some nice green tea. Maybe that's better. Or go to Phil's. That's really good. But that's a treat if you don't want to sleep for a few days. So, and the thing is this trick is so simple, right? But I had to read about it looking for something else. I was testing multipliers the old hard way, and then one day, I don't know what I was reading, and why I was there, but the trick popped out, And I thought, oh, this is a great application for 110. Now, I just want to bring it back to, no, I'm just going to draw it. Okay. On one of the exam questions, right, just to kind of finish off Laplace, is that some of them had an input like this, again, you know, and the output was like very close or, you know, slightly delayed and a little bit less. But it looked exactly like the sine wave at time equaled 0. But then there were some that the sine wave started up here and then evened out. And so what it is the cutoff of the low pass, right, which is 1 over FC is the time constant, right? The time constant was so long that it took time for it to get to where it was going. So this is like the Laplace part because the sine wave, the output is not existing for all time, right? It's changing and it's settling. But then here, it's a sine wave, right? And the amplitude and frequency aren't changing. Here, the amplitude is changing in time. So this is like the Fourier part, and then this is the Laplace part. But when you set the cutoff frequency right, you can't see it. And when you use the ADLM, even at 100 hertz, you won't see this. It'll settle, and it just, the oscilloscope keeps repeating, and it only shows you this. Okay. Well, let me say it differently. So a step response is Laplace because it does not exist and it exists. A sine wave is always there, right? So if you look here, it's 0, it doesn't exist. Then it does exist, and it takes time to settle. You can see the shift between Laplace and Fourier. Now here, yes, does not exist. Exists. But the time constant is such that it settles to the Laplace. You might be able to zoom in and here say, well, it's not exactly right. But, you know, by eye, it looks fine, right? And you can set an oscilloscope to just record in time, right? So record a millisecond and then stop. And let's say you have a reset, right? Then you would kind of be able to see it turn off and on. But if this sine wave is like a kilohertz and the cutoff frequency is relatively high, it happens so fast you won't see it. But actually, you could see it. Like if it's really slow, right? You're seeing the sine wave at one thing, and then it slowly settles down. Like you have a sine, you might see this, right? And then over time, the whole thing shifts to where it should go, right? You can see that. But even like if you're trying to measure something and there's some random noise you're trying to get rid of, you say average it, sure. And yeah, a low pass filter is an averaging circuit, right? Here's the integration part, and here's the averaging part. So I'm just gonna, I gotta hit other stuff. I'm gonna leave that be. Okay. Listen, I moved Fourier control here because it needs to be that way for lab, but I forgot to do it. So I just fixed it now. So if things look out of order, that's what happened. Oh, it's the circuits. Okay. All right. Let's all review. All right. So here's another application. I'm just going to lightly walk you through it. This is a triangle wave with some noise on it, and I'm modeling a pulse meter that the index of refraction in your finger changes with pressure, your heartbeat, and you send in an infrared sensor, and it modulates effectively a transistor. And this is what you get out. And so it looks great because I've zoomed in on it, but really the signal is quite small and there's a lot of noise here. Now, yeah, this circuit here is a way to drive an LED that it'll blink for your heart rate. So I take, what do? I take the FFT and I have a peak at a hertz, right? And I have an infinite number of peaks because the frequency of this is my heart rate. This just happens to be in triangle waveform. So triangle waves have corners, so they have infinite frequencies, right? So I want to keep my heart rate, let's say a hertz, right? So I want to do a band pass around that and get rid of everything else. Okay. Also, this is 1.7 volt offset. I really need to get rid of that DC, otherwise things won't work. So, oops. So what this circuit does here is this capacitor, like, basically it blocks DC, right? And yeah, here's now it makes a high pass filter going here. So it's blocking the DC signal, but then on the feedback loop, you've got a low pass with some gain, right? But it's a little bit tricky because this is not inverting compared to this. It's the circuit's a bit of a hack, right? They combine things, and then this is the LED driver, all right? And so what it does is it turns it into a square wave that blinks an LED on and off. Used to be a project we used to do. Now, half wave, this should be full wave rectifier. Anyway, my input is a sine wave. Oh yeah, then I convert it again with code. You can see the code that I use. It's all if this is greater, it's zero. If it's greater than 0, set it to Vn. If it's less than 0, set it to 0. All right. So here is my half wave rectifier. It's not a pure sine wave anymore because it's got those corners. And then I have VDC1 and VDC2. And these look the same amplitude, but look, this is changing from 0.8 to a little over 1, and this is, 0.98 to 1. So it has gone down. And if you look at the Fourier transform, here's the original thing at, probably I did 60 hertz. Now, yeah, there's some frequencies out here, and that's just digitization, right? Here's the first half-wave rectifier. Look at all the harmonics, right? The first DC, the harmonics are there, but it's less. And then the final, the harmonics again are still there, but I should say, LT Spice won't give you the DC part. It gets rid of it. So what you're seeing is this is the first harmonic, which you don't want. You want the DC, right? So now it's DC, it's not showing you, and then you filter it, and this peak, they all get smaller and smaller. So you can have a low dropout regulator, and you can have a full wave rectifier, and this is like an op amp in reverse, where it takes changes in voltage and current and makes it smaller, right? So if you get a half wave rectifier and then put it into this circuit, it will actually be pretty good. That's something extra. This is an example that comes with the LT Spice, is if you have one sine wave times another, right? We're going to go over this later, but you get another sine wave. You get two sine waves at two different frequencies because these frequencies are different. If the frequencies were the same, it would just double it. But what you do is you get this frequency plus VA, VB's frequency minus VA. And then this is a pulse. So it turns it on. So it's 0, and now you can see there's kind of like, you can see a larger pattern with one frequency and then something faster. So there's actually like, two sine waves there. So when you do the FFT, yeah, there's two peaks. If we looked at negative frequency, you would see two peaks at the negative frequency as well. That's more of the modulation thing, right? And I put in a filter, and I'm trying to get rid of one peak to get back one of the sine waves. Now these are so close, it's very hard. You can still see it rippling, right? So I use FFT, see what I want. I try to band pass it or high pass it or keep it, right? That's really that. Now the Butterworth filter. So just to kind of go back and all right. So this is a Salin key filter, low pass. But the R and C values can be for Butterworth, right? You can make it overdamped, critical, under, and Butterworth is when the damping is 0.707, right? So this Sallen and Key, even though we use Butterworth filter a lot, it can be whatever you want as long as it's second order, right? And then the multiple feedback filter can be Butterworth, and there's other architectures as well. So this is, oh, and then you have, I'm just going to say multiple feedback, but you also have this. So you have three ways of doing your filter: Sallen and Key, multiple feedback, and RLC. But then, so there's, we can just call that, that's the circuit architecture, right? Then you have what kind of filter? Low, high, right? And then you have, I don't know, we could just call it the style, which is one of which is Butterworth. So, all right. And they just had a nice picture. I just got to find it. Okay. So don't be confused. These are linear graphs. All right. So this is the Butterworth shape. Chebyshev type 1 has this shape. Notice how it's sharper. It oscillates a little bit, but notice how it's sharper and goes to zero faster. Then elliptical filters kind of are even sharper than that, but then they bounce up a bit. And Chebyshev type 2, it's kind of a trade-off between Butterworth and type 1, although it does bounce here. So these are all low-pass filters, and they're all, they can be all done with Sallen and Key, multiple feedback, or RLC. But how is that? There's just this picture I want to, or it might be on the other filter. Here we go. So this is a very interesting plot here, is that it's an analog plot of the complex and real planes, and these white parts are the poles, right? So I have a pole here, and then I have a pair of complex poles here, and notice that the phase difference is equal. In fact, you're supposed to put the other ones out here, so you split it all along the unit circle. And if you want a higher frequency, you just make the circle bigger, right? But you only use the poles on the left-hand side. But the algorithm is these poles are, if I have one, I put it here. If I have two, second order, I put it here, right? So that the phase, if I have 3, 4, and so on, and those poles, that's just how they're split. Okay. Now, what happens is the higher order the filter, the sharper it gets, right? But we want this band to be as flat as possible and then roll off, okay? The algorithm for that is right here. So S plus 1 right? That's one pole. S squared plus 1.41 S plus 1, that's a second order Butterworth filter. And yeah, you can tell that this term is 2 times the damping coefficient times omega naught, right? So the damping coefficient is 0.707, and so this is what you get. And if you want to change the frequency isn't, here the frequency is 1. This is the cutoff frequency. Here, this is the cutoff, this is the frequency term squared, cubed, and so on. So if you want to make, you're doing a cutoff at 10, well, I would put 10 here, but then I would have to put 100 here, 10 there, 100 there, and so on. You have to, but Python just, they can calculate that for you. It's well known, right? But this is the algorithm, okay? Elliptical has that Bode plot, and the poles are distributed in an ellipse. Now understand, you don't use these in your filter design, because if you did, it would be out of control. Um, then there's Bessel. It's got a slightly different thing. But the key point is that you are, whether it's high pass or low pass, right, you have a very bad looking unit circle. So the bigger the circle, the higher the frequency. But you can kind of come up with your own algorithm. So the Butterworth, right, it's trying to evenly distribute things. As it goes on. So it's trying to distribute it like that. And then you saw with the elliptical filter, right, it's splitting it, but it's elliptical. So another algorithm. All right, here's a square algorithm. And you say, well, if it's an odd, there'll always be this one here. And then you find your own algorithm where you split it, or then you do that. Okay, you come up with your own way that you can keep following it, right? Or maybe, right, this is first order, second, third, and it's just along a unit line like that, okay? Um, something like that. That's a sideways heart. Feel free. So there's a homework assignment where I want you to come up with your own algorithm for a low pass filter, right? And see what happens. Okay. You could be the next Bessel or Mr. or Mrs. Butterworth or something. Okay. Could be. Huh? Right. I haven't been sleeping well lately. So, but yeah, here are the, elliptic is like a shape. Oh, it's got a person's name. Gaussian is definitely somebody's name. That's a name. Those are names. So one day, Naomi, see her name right there. Okay, on Wikipedia, which I pay for because I use it all the time. Yes. Okay, thank you. And since you pay for it, you're rewarded by being asked to pay for it. That's okay. Oh, right, and here's no, that's the old homework. Okay. So that one really, it's a lot of work, but it's for fun. There's no way I can put that on the exam unless that is the exam. All right. So I know some folks need to concentrate, right? But just go draw your own shape and try to come up with an algorithm for it. Do not use this, like I have an example, right? And I think it's this one. Or it's like this. Something like that. Well, it can't be there, it'd be out of control. It can't be here because it would be out of control. But don't use the example, just create your own. And I'm just looking for effort. Like, is it really the algorithm? I don't know. It would take so much effort for me to determine if it really was the algorithm in question. So it's up to you. So that's really it. And now you've kind of seen everything that I use. Like, now you know the Butterworth algorithm, what's going on, and the other ones. So now when you're using the analog wizard, well, you know what's going on. When you use Python and say, give me this filter, you know what's going on. But yeah, do it from scratch if you're trying to really understand it. But you can use those constant generators, just fine. You've seen three circuit architectures: RLC, multiple feedback, Salin and Key, right? To make low pass filters. And now you can adjust the constants, and you can even, high and low pass are fine too. I think the wizard, right? There's high pass, low, and band. It doesn't do notch. And I think what you do is if you want a fourth order notch, right? You do a second order high, second order low, and cascade them. But this would be, for Butterworth, that damping coefficient would be 0.707. This one would be, so you have to, it won't just give you, because a fourth order notch is really a second order high and a second order low. The band can be fourth order, but because, like a fourth order filter, that'll be 40 and that'll be minus 40, because you're going up and coming down for a total, where a fourth order low pass will be minus 80, right? Well, with the notch, it's the same thing. You would get 40, 40, because it splits it. And when I first thought it, like, I want a fourth order filter on each leg. No, it splits it. And if you put in an odd number, oh my God, don't do that. Don't use odd numbers it works for the high and the low, but the bands, actually Python will just give you what it thinks is best. It won't let you do odd. And how could it? Because you got two things going on, so it can't be odd. All right. Hmm. Link to extensive problem set. Oh wow, that was a busy beaver. So here are like, I just made up every conceivable impulse response, and you just go through and say high and low, right? If there's a delta function, it's high. If not, it's low. Oh wow. Interpreting the step response. Hmm. Let's look. All the plots below are step responses of various, which are high pass and which are low pass. Okay. So the step response is going to start at 0 and end at something, right? So a low pass passes low frequencies, or DC. So for a low pass filter, if I put in a 1 volt step response, I should see something like a volt coming out over here, right? And the high pass passes the edge and blocks DC. So this is high at the beginning, like an edge, right? Step function has an edge. That edge is passed through and it goes down to 0. So this one is high pass, right? This one starts low and is passing this DC signal, right? So it's not a shape we're used to, but it's a low pass. Again, this is an edge, starts high, decays to 0, starts low, and goes up to 1. So high, high, low, low. Edge, edge, you know, rounding, 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 passing DC, low, low, high, high. But this one was really hard to program. But anyway, start slow. And now again, it could go negative voltage, right? But it's stabilizing at non-zero. Weird shape to get there, but stabilizing at non-zero, stabilizes at 0, stabilizes at 0, passes the edge. So high, high, low, low. Edge, edge, rounding, DC, DC, 0, 0, so high, high, low, low. All right, people tend to do these well, so no, I'll include it, but I don't think I need to go over it, okay? You guys, so then, Bodie plots, we just did that, derive, let's see. We just talked about controls, so design a filter, people do really well on that. Find the issue. Uh, okay, so this is a inverting, right? And so from this spot there, right, I'll just call that Vx. V out over Vx is simply 1 plus R4 R3. Then we'll call this Vx1, right? Vx over Vx1. It's voltage division, right? I'm just going to give you the answer. R5 C2, R5 C2. Okay. Now over here, it's inverting. These two here, they determine the cutoff frequency, right? So the pole is due to these two. All right. I'm running out of time, right? But at low frequencies, right, this capacitor becomes infinite, and then it just becomes a inverting amplifier, so you get minus R2 over R1, right? And yeah, then I remembered, oh, that's what it is. Okay, because we're in a rush. Then you multiply all of these together, okay? And then, yeah, we're out of time, so there's derive it, and then there's do the Bodie plot, things like that. All righty, have a good day.